Hello and welcome guys. Now in this video we will be implementing all the assumptions that we have discussed in the previous video. So we'll see whether these assumptions that we have discussed whether make sense or not. So let's dive into it. So for the very first assumption was the linear regression assume a linear relationship between the independent variable and dependent variable. Okay, so let's implement that. Okay, so we'll use numpy and matplotlib to see that. Okay, now we'll create a synthetic data. So for that, let's define x equal to np dot linspace 1 comma 10 100 data points. Then y equal to 2 multiplied by x plus 3. Cannot let's take normal 0 comma 1 comma 100. Okay, so we have defined our x and y. So let's see how x look like and then y. See, okay, so we have our x and y ready. Now let's plot it using scatter plot. Okay, so we have plotted our x and y data, and and we can see that in data x and in data y we can see the relationship that we see is linear. So we have proven that assumption 1 is correct. Okay, and the data x and y have we can clearly see they have linear relationship. Now let's move to assumption 2, that is let's say it is independence of error. Okay, so so the error should be independent of each other. It shouldn't be very different or very close. It should be independent of each other. One shouldn't be dependent on the other one. So let's implement it. So again, what we need is we need to use the same libraries, as well as we need one more, that is stats model. So import stats models API as sm. Okay, so let's move ahead. So again, here we will create synthetic data. So let's say our x is this. Okay, and our y is this. Now one more thing that we have to do is we need to introduce autocorrelation for y data set. So let's do autocorrelation for 50 onwards rows. One comma 51. Okay, so now let's see our y. Okay, so this is how our y look like, and you can see that after 50th data point we have introduced some of the correlation. You can see that most of the data on the left side is matching with the right side. Okay, so we have introduced some correlation. Okay, here in the y data set. Now what we need to do is we need to add some constant in the x data set. Okay, so x equal to sm dot add constant, and here we will pass x. Okay, now model equal to sm dot ols y comma x dot fit. Now let's plot the scatter plot. So let's copy this. Okay, and here we will pass model dot predict model dot resid. Okay, this only residual. Now assumption 2, independence of error. So basically this independence of error also uh, means that the error for different data points should not be systematically related or correlated with each other. In other words, the presence, or you can say magnitude of one error should not provide information or influence the presence of or magnitude of error of other data points. So this assumption is important, and it is to ensure that the statistical property of you know estimated regression coefficient are valid. So if the errors are not independent, what it will happen, it will lead to bias coefficient estimate, unreliable hypothesis test, incorrect inferences. So specifically, if there is a autocorrelation, which is basically correlation between error at different data point, it can indicate that the model is not capturing all the relevant information in the data, and there may be omitted variable or other issues, and that's the reason we have added autocorrelation to see it. So this assumption of independence of error doesn't imply that all error must be same size or uniformly distributed around zero. It means that error should not be exhibit any systematic pattern or correlation with each other. Error can be close to zero, far from zero, or or have varying magnitude, but they shouldn't be exhibit a predictable structure. That is what it says. Okay, so let's complete the implementation. So here x label should be predicted values, y label should be residuals, and then plt dot show. So the result that we see, so basically you remember, right, we have introduced autocorrelation in these data that we have generated by adding linear trend to error after certain point, that is from 51st point onward. So the resulting scatter plot that you see here, predicted value versus residual, indeed show a clear pattern resembling a V shape. This pattern is a strong indication of violation of independence of error assumption in the linear regression. So the V shape in the scatter plot suggests that the residual are not randomly distributed around zero, but rather exhibit a systematic approach, or structure. So in this case, the residual appear to have a positive correlation, meaning that they are positively correlated with each other in a systematic way. So this is not consistent with the assumption of independence and identically distribution of error, which is important for the validity of linear regression. So in practice, if we encounter such a pattern in the residual, it indicates that the linear regression model is not capturing all the relevant information in our dataset, and that is what I wanted to show you. To prove this point, that if we get something like this in the project or some experiment we are doing, this means this shape is basically violating the assumption 2. Now let's implement this error again without autocorrelation. So here we have implemented autocorrelation, to just wanted to show you that, that's why. Okay, now let's copy all this same code. Okay, so just remove this point and everything will be remain same. Okay, so let's run it. Now you can see that every error is uh, not in a clear pattern, or you can say the predictable manner, and this is like a strong indication that it's not violating our assumption 2, that is independence of error. Okay, so let's move to assumption 3 now. Okay, that is our homoscedasticity. Okay, okay, homoscedasticity. Okay, yeah. Okay, same thing. What we need is all this libraries will create our data. Just copy this x and y. Okay, now one more thing, we need to introduce homoscedasticity here. So I think this particular code just need you know a little changes, x into p dot random normal. Yeah, this is fine. Introduce let's run it. So if you want to see your y, you will see some random variation. Okay, so now again what we need to do is just copy this code, paste it here, x and y. Now same thing, just change this assumption 3. So basically what our assumption 3 says is that linear regression assume that the variation of error is constant across all level of independent variable. Okay, so let's see it. So what this plot is saying is basically so you remember we have generated data with uh, with introducing you know uh, okay, we have introduced heteroscedasticity here. Okay, not homoscedasticity. Okay, and that's why, so basically what we are seeing here is, so just remember guys, so in a scatter plot, if the spread or the dispersion of the residual is fairly constant and it doesn't exhibit a clear pattern as you move along uh, the predicted value, it suggests that the assumption of homoscedasticity is met. On the other hand, if the spread of residual systematically change as you move along the predicted value, it indicates that heteroscedasticity, which is a violation of assumption. So when we have introduced heteroscedasticity in our synthetic data, the scatter plot that we are seeing is like a fan, or you can say cone like shape. So in the context of our code, the scatter plot or predicted value versus residual is used to visualize whether the spread of residual varies with the predicted value or not. Okay, so in summary, if we see structure like this fan or cone like shape in the scatter plot, it suggests that the residual variance is not constant across all level of the independent variable, indicating a violation of homoscedasticity assumption. So to address this, what we will do, again just copy this whole code, paste it again. Okay, we'll remove this x into basically that I did because I wanted to show you uh, how the violation look and how without violation it looks. So we have removed our heteroscedasticity. Now let's run it again. We'll fit the model and then run it. Now you can see that it's not cone like structure. Okay, so that means that our assumption has met it. Okay, so since the chart is since the data that we have generated is not more like linear, but remember that the the graph should be like this one. Okay, so this means that our um, you know our assumption has met the condition. Okay, so this is what it says. So hope you guys have understood all these three assumptions. Just remember that this shouldn't be like this, it should be like linear. Okay, okay, now let's go to assumption 4. Okay, so what we will do is, let's name it normality. Oops. So it basically says that linear regression assume that the error follow a normal distribution. Okay, so again same libraries. We also need here scipy. Okay, since we have already imported, we do not need. Okay, let's create our synthetic data. Okay, we'll copy the same thing, and here again first we will see how the opposite version look like. So we will do like adding non-normality to this data that we have. So what change is required is np.random.uniform. Okay, okay, so what we have done, we have introduced non-normality. Okay, let's run it, copy this code, paste it. Okay, and also one more thing, uh, we do not need this. We will plot probabilistic plot. Okay, probabilistic. So residuals equal to model dot resid. So here introducing. Okay, so let's run it. So okay, let's plot the other one also, so that it will be clear for me to explain. Again, we have to remove the uniform to normal. Okay, okay, both the plot looks same. Okay, let me explain what is the difference. So in the very first plot, what we have what we are seeing is this is a QQ plot. Okay, and QQ plot is used to plot residuals, or you can say probabilities. Okay, so basically this plot is, so guys, what we see in these two plots are basically the QQ plot. Okay, let me tell you what QQ plot is. So QQ plot is useful tool to assess the normality assumption, and in our case it's effectively demonstrating the violation of the assumption 4, okay, due to non-normality distributed error in the synthetic data. So basically, if the QQ plot shows a clear departure from the straight line, like for example points bend upward or downwards, okay, like we see for this case, okay, it indicates that the residual are not normally distributed. In the context of our code, the the QQ plot is likely to be show a departure that we are seeing here, and obviously because we have introduced some non-normality in the our synthetic data. Okay, so that is what it is saying. Also, one more thing that wanted to clear out, that is the QQ full form is quantile plot, and it is used to assess whether a dataset follow a theoretical distribution such as normal distribution. It helps us visualize the relationship between quantiles in a ordered value of the data and the quantiles that would be expected under a specific distribution. So in a QQ plot, the x-axis represents the quantiles of theoretical distribution and y-axis represents the quantile of observed data. If the data follow a specific theoretical distribution, the point in the QQ plot will roughly fall along a straight line that we see here. It's almost straight line. Okay, so deviation from straight line indicates departure from the assumed distribution. So how it basically works, so I mean, we would expect our data to follow a normal distribution. In case of QQ, we would compare the quantiles of data to the quantile of normal distribution, where mean should be 0 and standard deviation should be 1. In this case we can see that, but not in this case, because if we look at standard deviation, we will see that the standard deviation is not close to 1. And if the point in the QQ plot deviate from the straight line, it suggests that data doesn't follow a normal distribution. You can see here. So that is what just wanted to clear, and it's not clearly a uh, plot probabilities plot. Instead, it helps us assess whether the observed data conforms to a specific theoretical distribution by comparing quantiles of the observed data to quantiles of theoretical distribution. So it's a very helpful tool. Okay, now let's move to our fifth assumption, so that we will be covering in the next tutorial. That is with I will also explain VIF. So VIF is variance inflation factor, and that is also used for feature selection. So let's cover that in next video. So thanks a lot for joining. Hope you like this video.